Yeah. So in the last lecture, what we have introduced is the differentiability of function of two variables. Okay. Let me take you back to the definition. Okay. So let me have the definition here. Yeah. So it's clearly says that a function is differentiable at a point x naught y naught if certain things happen. Okay. So let me erase this completely. Yeah. So some of you might have questioned that how will you check the differentiability of a function of two variables? Then obviously it will lead to the other definition for differentiability of function of 3 or 4 or 5 variables and so on. Okay, so as I told, this can be extended to those the further dimension. Okay, in the similar manner. Okay, right. So this is a definition here. Let me take you here. So a function z is differentiable at a point x naught y naught. So what it says, if you have the increment in z direction, it can be expressed in the following form. When you look it on the right side, it's nothing but a linear combination of, or not, I can't say this is a linear combination, okay, but it's a combination of this first order partial derivatives and increment in x direction, y direction, and some weights here epsilon 1 and epsilon 2, which are tending to 0 as both delta x, delta y tends to 0. Okay, right. So if you are able to express the increment in z in the following form. So if you concentrate on the right side, what it involves? It involves the first order partial derivatives. So the necessary thing here is, first thing that what you should check is the first order partial derivative exists at the, then only this right hand side expression is valid. Otherwise, no. If they are not exist, they do not exist, they do not exist, then the right side expression is not valid anymore. Right? So this is why here the condition is already clearly says that fx and fy first order partial derivative exists. Okay, right. So the gist of this definition is, if you are able to express the increment in z, when your means increment in z is z equals to f of xy, you are means z plus delta z is equals to f of x plus delta x in the both the direction you are incrementing, right? And then you're taking the difference. That will give you the delta z as the left side. Okay, that's the left side. Now, if you are able to write this increment in the following form, then we say that the function is differentiable. So this is a mathematical definition to justify some of the things, like how will you get down to the it's like the properties which you have learned for one variable cases, they should not lost. Okay, and you can now you can generalize this definition to the more than two variables. Okay, in the same direction, you can include one more variable and you can do that. Okay, now, so we have also mentioned the sufficient condition, okay, for differentiability of function of two variables. What was that? If in addition, this first order partial derivatives, if they are continuous, then you can straightforward tell that this function is differentiable. So this was you can have, this is an increment theorem, or you have, this is what we were not interested in proof here again. Okay, if you want, I may share you the proof. Okay, but right now we are not going with the proof of this result. Only we need to understand this sufficient condition. Okay, so this is, I'm again mentioning here, it's a sufficient condition. Okay, this is sufficient conditions for differentiability of function of two variables. So some of you, I think one student also have emailed that how would you verify that the function of two variable is differentiable? So here is that that result you can have, means you need to check the continuity of first order partial derivative at that. If you are able to verify that first order partial derivatives are continuous at that point x naught y naught, then you can straightforward refer this theorem, or you can say immediately you can treat this as a definition and say that this function is differentiable. Okay, so now this result, if you are going through the proof, okay, this result can be extended to more than two variables as well. Okay, so you have the answer for more than two variables as well. Suppose you have three variable function. Okay, if you have three variable function f of x comma y comma z, three variable functions, that if you want to say that function f is differentiable, okay, then you need to check the continuity of all first order partial derivatives, all possible first order partial derivative. Means you are checking differentiability at a point, so at x naught comma y naught comma z naught, one more. Okay, so you need to check the continuity of the function fx, fy, fz at x naught, y naught, z naught. If that is there, that function, original function, is differentiable. Okay, so this differentiability, as we have already seen, if you lie down to the function of one variable, that is a you are getting that particular case here. Okay, there is so point now. Okay, so I think I have cleared your that basic confusion, that means how would you check the differentiability of function of two variable or three variable and so on. So what you need to look at is the means at some point x naught y naught, okay, or x, which is the three dimension x naught y naught z naught. So you need to look at the continuity of the first order partial derivative. Okay, so there is you see now, if I say there is no need to memorize these things, okay, right? Because if you have, suppose, n number of variable, okay, f is a function of n number of variable. If you want to say it is differentiable at some point, you have this is x1 comma x1 comma x2 and so on xn. What you need to check is simply that all the first order partial derivatives at x1, x2, xn, okay, they are continuous at that point, whichever you are checking. And suppose you want to say the function is differentiable throughout the domain, means you need to verify that the function, that first order partial derivatives are continuous over the entire region. Okay, then you will say the original function f is differentiable. Okay, so this clarifies your doubt. Okay, let's move further. Okay, so of course we have also had that that result which we had seen in function of single variable as well, that differentiability of a function of single variable implies the continuity. So here also it is very easy to verify. Okay, that I can left as an exercise to you. It's a very easy to verify. If not, it will take only one or two steps. So try to get that feel. Okay. Okay. So this, whatever we are talking about right now, again, I'm mentioning that the function of two variables, that similar way you can extend it to the function of three variable, four variable, and so on. Okay. Now, in the function of single variable, we have seen, suppose you have y equals to f of x. Y is a function of x depending on x. X is independent variable and y is dependent variable. And suppose x is still, it's not independent, it's a function of t. It's a dependent. So what it says, y is implicitly is a function of t. If you replace x by g of t here, so function y, you can find out y is a function of t itself. That's also possible. Okay, but when you are extending in the dimension, so you will see that is not a good idea to replace it. Okay, because you have alternate. Because okay, that may lead the complexity of the problem. Okay, means you will need to find go for more steps. Okay, when you are solving or when you are attacking the problem, that we will see. Now, what is my interest here is, suppose I'm interested in finding the dy by dt. Okay, so I'm interested in dy by dt now. So y is a function of x, x is a function of t. So how would you differentiate? It's going to be f dash first, and then dx by dt, right? So what is dx by dt? Is g dash of t. So it is going to be f dash of x times g dash of t. So what we ever know aware about this rule is, this rule is known as chain rule, right? So similarly, you can have the extension to the function of two variables. So suppose you have now a z equals to f of x comma y. It's a function of two variables. Okay, let's suppose you have x equals to some function of t, let's say h1 of t, and y is equals to some h2 of t. And I'm interested in dz by dt. So certainly what you require, okay, at the first step, what you require to verify whether z is differentiable or not. Then only you can talk about this. But we have the answer for that as well. Means suppose if f is differentiable, when you say that function is differentiable, is whenever its first order partial derivatives are continuous. Okay, and moreover, because you are interested in dz by dt now, so what you require in addition to that, first order partial derivatives are continuous, you need the differentiability of the function x and y as well, right? So if everything is nice, okay, if everything is nice, so suppose dz by dt is exist. Okay, then now if you look at back that increment theorem, what was that? Is delta z is equals to fx. Let's somewhere at point. Okay, so delta x, I'm not mentioning that, fy delta y plus epsilon 1 delta x plus epsilon 2 delta y. Right? So if everything is fine. And what you are interested in d by dt, so you divide both sides by the increment in t direction delta t. Okay, so delta t. Now apply the limit delta t tends to 0. Okay, so applying limit delta t tends to 0 will give you the answer. So what will be the answer here is, I'm just going to replace now. This answer is fx times dx by dt plus fy dy by dt. Right? Right? And rest of the things. So this is dx by dt and dy by dt. As you know, as delta x, delta y tends to 0, this epsilon 1, epsilon 2 also tends to 0. They are very negligible quantities. So when you are applying the limit delta t tends to 0, they will not contribute anything. Okay, so this is going to be the chain rule. in the function of 2 variables. So this can be extended to the function of 3 variable, function of 4 variable, and so on. Okay, right. So here I have this this result which is named as theorem. Okay, so if this w is equals to f of x, y has continuous partial derivatives, which I mentioned, first order partial derivatives, and x and y are function of t and they are differentiable function of t, then everything is fine and you can find out dw by dt by that. Right? Now, this can be extended to the 3 variable case as well. So if you include one more variable, it will give you the result. Okay. So I think I have that here. So you can understand more this by using this tree diagram here. Okay. So here w is equals to f of xy. Your goal is to identify dw by dt. So first you differentiate w with respect to x and then x with respect to t. Similarly, w with respect to y and then y with respect to t. So they are, see, this side is simultaneous task. Again, if you go back and look at some probability concepts. Okay. So simultaneous task occurs then in the product rule. Okay. So dou w by dou x into dx by dt will be the first term. Another is this side, dou w by dou y into dy by dt. Now you can increase one more dimension. Then if you have one more z, so you have this is that you can have, and so on. You can increase how many number of variable you will want. Okay, and when you don't have the simultaneous task, they are okay. Then you have the sum rule here. Okay, but they are falling into the case. Okay, so dw by dt is going to be a chain rule. So function of 3 variable. I'm not explaining anything. I'm just going to read this now. It's very much understandable now. So if w is equals to f of x, y, z is differentiable, x, y, and z are differentiable functions of t, then the composite w is a differentiable function of t and this. Okay, so you have increased one more direction, that is with respect to z. This additional term will be there. Okay, so if you try to see, let's say, so let's say w is equals to denotes the temperature. Okay, x comma y comma z, and x is a curve, is x of t, y of t, z of t. So then x equals to x of t, y is equals to y of t, and z equals to z of t. Then this composite function w, if you replace x by x of t, y of t, z of t. So if you draw this curve in x, y, z space, it's going to be curve, right? Okay, so this will give you the, this will be temperature along the curve, related to the curve. And when you talk about the dw by dt, it's going to be giving the rate of change of the temperature along the curve. Okay, so so we will we have this maybe in example I have some problems, okay, where you will find out different type of curves, okay, along which you can say along that path some particle is moving, okay, or that is a wire modeled in that fashion and temperature is passing through it, okay, or electric current is passing through it, okay, and so, or you are heating that wire, okay, at certain temperature. So see, that will be some type of physical interpretation of this a composite function. You can take it as this. Fine. Now, this is a chain rule function of 3 variables. I think I no need to explain this. It's very clear. Okay. Now, so suppose, so just now I have given you a very, very simple, okay, physical interpretation of that composite function. Let's say along a curve. Okay. Suppose you want to look at the temperature over a globe in a space. Okay. So means you have in the space, you have some you can say rectangular plate is there. Okay, you want to see the temperature along that plate. Okay, so then what you can look at is x. This is x, y, and z. Okay, so then you have w is equals to, let's say this is t of x comma y comma z. So along the rectangular plate, if you want to see, so what you can look at that x as a function of 2 variables. Okay, so some let's say r and s here. Y also you can look at as a function of 2 variables, and z also as a function of 2 variables r and s. So if you talk about the particular problem, so you can also look at, suppose you are looking at temperature at some planet, okay, other planet. So what you need to have, so you should have its longitude and latitude. Okay, so those 2 variables you can represent, let's say r and s. Okay, and then you will later on you will realize, okay, or that if it is correctly modeled, if you have this function correctly here, then you will have that temperature in your hand at that planet. So how would you look at suppose you are interested in now finding dou w by dou r or dou w by dou s. Means you are looking at the change of W temperature with respect to longitude or with respect to latitude. Okay, so how would you proceed? So again, so when you are looking at dou W by dou R, keep S as a constant. When you are looking at the dou W by dou S, keep R as a constant and apply the previous technique what we have adopted for explaining the chain rule for along the curve. Because when you fix S, suppose you fix S is a function of 1 variable. If you fix R, again, is a function of 1 variable. You can apply the similar technique as previously mentioned. Okay, so it's I think it's very clear. So you are going to first differentiate T with respect to R, then you have X, but X is a function of 2 variables. You have to differentiate X with respect to R. You can only talk about its partial derivative, not dx by dr. Similarly, dou W by, so if I write, let's say, so if I'm interested in dou W by dou R, so you need to differentiate T with respect to X and X with respect to R plus T with respect to Y, then Y with respect to R. Similarly, T with respect to Z, and then Z with respect to R. So this will be the corresponding rate of change. Similarly, for dou W by dou S, if you just replace R by S here, you will get that formula. Okay, so again, that can also be explained in the similar fashion by using the tree diagram. Okay, and again, so what changes we have observed here is instead of dx by dt or dy by dt and dz by dt, you have partial derivative now, not total derivative. Why? Because x is not a single variable. There is x is a single variable function. Okay, right. So so again, you need to attach some nice things along with the definition of the functions now. So for talking about all these things, what you require is all the functions, these all w, x, y, and z, all should be differentiable. Okay, then only you can talk about. Okay, so this is clear. I think we don't need to discuss more. So this is a chain rule. Again, if I have here, W is dependent variable. X, Y, and Z, which they are not independent, they are depending on R and S. So you can we will say them that as these are intermediate variables. Okay, and R and S are independent variables. Now, if you talk about dou W by dou R, so again I told you dou W by dou X into dou X by dou R, dou W by dou Y into dou Y by dou R, dou W by dou Z into dou Z by dou R, and perform the subgroup. Similarly for dou W by dou X. Okay, right. Fine. So you have this these three problems here. Okay, let me handle one or two. So first question, that use the chain rule to find the derivative of W equals to X into Y with respect to T along the path X equals to cos T, Y equals to sin T. What is the derivative value at T equals to pi by 2? So it is already mentioned here, you have to use the chain rule. Otherwise, you have method, right? You can replace X by cos T here, Y by sin T, and you can directly differentiate and find the value at T equals to pi by 2. Okay, it will not change the scene. Okay, so if I talk about this first problem, so I have been given with W equals to X into Y. Along with X is cos T, Y is sin T. And you are talking about at T equals to pi by 2. You have to find dW by dt at T equals to pi by 2. Okay, right. Now, for finding dW by dt, what you need to verify? So W is differentiable function. It has all first order continuous partial derivatives, right? Wx is what? Y. What is Wy is x. They are continuous functions everywhere. X equals to cos t, y equals to sin t. They are differentiable. So all the conditions are satisfied. You have to verify that. Now, by chain rule, dw by dt is equals to dou w by dou x times dx by dt plus dou w by dou y times dy by dt is equals to. So this is y into dx by dt is cos t derivative is minus sin t plus dou w by dou y is x times dy by dt is cos t. Now, if you replace x by cos t and y by sin t, you have cos square t minus sin square t. Okay, so what is implies is dw by dt is equals to cos square t minus sin square t, and by trigonometric formula it is nothing but cos 2t. Now at t equals to pi by 2 you are interested in, so dw by dt is equals to cos pi, and that is nothing but minus. Okay, I think these exercises are simple for you. Okay, now yes,
Sir, instead of doing the chain rule, can we just do trigonometry, because x into I will become sine 2t by 2.
Okay, so before starting I have mentioned that when you are asking with the subjective question, say if see, you can do in your notes in whatever way, but whenever it is asked in the exam like subjective question, you have to use the chain rule, means you are forced to use the chain rule. If it is not mentioned, like you have straightforward asked to find the derivative of this, you are free to choose your path. Okay, did you understand my point?
Yes, sir. Thank you.
Okay, of course you can do direct as I told already. So it's a, when you have mentioned this, you are forced to apply. Okay, right. Now, I think this second problem you can do. Find dw by dt if x w equals to this. So there are both ways. X into x, y, and z you can put down here as straightforward. You can find out if it is not mentioned. Now, Similarly, here in the third problem, I will do what dou w by dou r. I will leave dou w by dou s for you. Okay, so w is equals to x plus 2y plus z square. Okay, so let me have this third question. W is equals to x plus 2y plus z square. Right? Yeah, x equals to r by s and y equals to x equals to r by s, y is equals to some r plus ln of s, I think, r square plus ln s, and z equals to 2r. R square plus ln s, z equals to 2r. Now, you need to check all four functions are this w, x, y, and z, all are differentiable. So very first, so for w, you need to check the differentiability. What you have is you need to check the first order partial derivative. Wx is 1, wy is 2, wz is 2z. So they are nice functions, right? They are continuous. Now, x, y, and z. So z, there is no problem. They are differentiable. This is a differentiable function. Okay. What about y? Y is also differentiable as long as you will not consider that s equals to 0 or negative of s points. Right? Similarly, here x equals to r by s. This is a rational function. Both are continuous. It's only discontinuous at point s equals where denominator get vanish. S equals to 0. Okay, so let's consider that all the things are fine, means the domain is created in such a fashion that nothing trouble is here. Okay, no trouble is here. Okay, so then you can proceed with this x, y, and z. So you require now what? Dou x by dou r. So I'm interested in now dou w by dou r. So that's going to be dou w by dou x into dou x by dou r plus dou w by dou y into dou y by dou r plus dou w by dou z into dou z by dou r. So all things are in your hand. Dou w by dou x is wx, that is 1, into dou x by dou r, that is 1 by s, plus dou w by dou y is 2, dou y by dou r is 2r, plus dou w by dou z is 2z, into dou z by dou r is 2. Now you simplify it. Okay, and so what you find is this implies dou w by dou r is equals to 1 by s plus 4r plus 4z. Now z equals to 2r, you can replace it. So 1 by s plus, so 4 into 2 is 8r, 8 plus 4 is 12. So this is a final expression in r and s. So either you leave it in the r and s form or you leave it in x, y, z. Okay, right. So similarly, you can find dou w by dou s. I think that's not required discussion here. Okay? If it is required, we will see in the tutorial. Okay. Now, what is this chain rule will give you very interesting thing that's called implicit differentiation. Okay, means when you have suppose you have a function of two variable x comma y that is equals to 0, and here note that y is depending on x. So indirect, so see, it looks like it's a function of two variable. Okay, but implicitly y is depending on x. Now the question is, I'm interested in finding the dy by dx. Okay. See, it will be very difficult when you have very complex equation. Okay, complex means very equation which cannot be simplified. Okay, means if you are not able to simplify this as this, then how will you find out dy by dx? Okay, so that answer will be given by the chain rule. So for applying the chain rule, what you require, you are treating x as a function of x, y also as a function of x. Okay, right? And treat f as a function of two variables and assume that this capital F is differentiable, means first order partial derivatives are continuous. So if everything is nice, so the derivative is 0. df is, let me have another page. Okay, so let f of x comma y is differentiable. W is equals to f of x comma y is differentiable. Okay, now then dw by dx, I'm interested in the finding the derivative with respect to x. Okay, right? So dw by dx is df by dx, means that's going to be this, and when you are applying the chain rule is going to be dou f by dou x times dx by dx plus dou f by dou y times dy by dx. So dx by dx is 1. So you have, this is fx plus fy times dy by dx. So if you choose f of xy equals to 0, then dw by dx is also 0. Derivative rate of change is 0. So that will give you this. You can simplify that put equals to 0. That will simplify that dy by dx equals to minus fx by fy, provided fy, this dou f by dou y should not be 0. Okay, so now if f of x comma y equals to 0, then certainly dw by dx is also 0. So this implies fx plus fy times dy by dx is 0. So this implies dy by dx is equals to minus fx divided by fy, provided fy should not be 0. Otherwise, this is not valid. Right? This will not give you anything. So this is the application of, you can say, chain rule here to do implicit differentiation. Okay? Right. Right. So this is the result theorem which I am talking about, implicit differentiation. Suppose that f is differentiable and that the equation defines y as a differentiable function of x, then at any point where fy is non-zero, dy by dx can be obtained by just finding out the partial derivatives. Okay? Right. Okay. Now, see, in the case of function of single variable, y equals to f of x, we have talked about the maxima, minima, right? Maxima and minima of function of single variable. Okay. So in the xy plane, particularly what we were looking for is a curve y equals to f of x. And in more particularly, we are looking for the absolute, not absolute, local maximum, local minimum. Okay. So what we are looking at in the single variable case by finding at the local maximum, local minimum, is we are looking at the tangent which is horizontal, okay, or parallel to x-axis. Okay. Similarly here. Right. So this will be point of extremum, and this is also point of extremum. That we are also aware about interior extremum theorem, which tells you that if if you have an interior point, okay, A comma B, that's an interval. Let's take C belongs to A B. So F has a critical point or extremum point at C if its derivative exists and it is equals to 0. We have seen that F dash of C is 0. Interior extremum theorem, if you recall it. And you have also seen that boundary points are also will be included at the as the critical points there. Moreover, where the function fails to be differentiable at the point, that those points are also we have included in the list of the critical points. Now, what will be the possible generalization in the function of two variables? Okay, so in the we are going to look at the tangent plane. Okay, right? So we have not. I think I hope in the during your preparation ITJ or somewhere in your it's like +2 standards, you know, you are aware about tangent planes. Are you aware about that? Are you aware about tangent plane normals? Can anyone answer? Am I audible? Am I audible?
Yes, sir.
Yeah, so can anyone answer that? Okay, are you aware about the tangent plane normal to the surface, something? Somewhere in vectors?
Means normal to the plane we have heard.
Normal to the plane or
Means
normal
we
to
are
the surface?
yes.
Normal line, tangent plane. Okay, anyway, fine,
sure.
it's okay. I can just simply just giving you idea. Maybe later on we will have that in our syllabus also somewhere. Okay, if you have this is here x, y, z space. Okay, and you have z equals to f of x, y. Let's take this as there. Okay, and let's take this is your x naught comma y naught. Fine. So the corresponding this here you will have the point like x naught comma y naught comma z naught and what z. Okay, let me write down z. And this is the surface z equals to f of xy. Now, what do you mean by the tangent plane is nothing but the horizontal plane is parallel to, you can say, xy plane. Okay, passing through this. Fine. Passing through this point, it's a kind of a rectangular plate, you can say, horizontal to the xy plane. Okay, and how would you identify the equation of this tangent plane is you have to identify the normal, because you know if you have the normal to the surface which is going upward, if you look if you try to look at geometrically, you just have a bowl, you can say. Okay, bowl is reverse bowl. Okay, downward. And if you are looking anywhere at any portion, okay, so what is the normal is to that ball is upward direction or inward direction. Okay, either inward direction or outward. So outward we are talking in generally. Okay, so inward means pointing outward, which is going to be orthogonal to the tangent. So tangent plane is that nothing but the rectangular plate, you can say. Means you have this rectangular steel plate you can take, and anywhere you can put it down. That is a, and along that tangent, along that rectangular plate, you will have the normal in the upward direction. Okay, so here you can maybe I have not drawn those. This is ball I can, okay, that is, let's see this as a part of the ball. Okay, let's see this as a part of the ball. Okay, and this is a rectangular plate sitting on surface. Now, what is the normal? Normal is in the upward direction. It's normal. So this normal will have this is a vector. You can have this is fx in the x direction, in the y direction, in the z direction. You have minus z equals to z minus f of x y equals to 0 in first order partial derivative, if you recall. And any point in the tangent plane, this may also repeat, okay, in some maybe later stage as well. Okay, suppose you have take any point in this tangent plane, x comma y comma z, any point. Now this line, so this line, this vector has the component is x minus x naught, y minus y naught, x minus x naught, y minus y naught, z minus z. So any vector in this tangent plane is going to be the perpendicular to the normal. Okay, so the dot product with this fx, fy minus 1, this vector will be 0. That will give you the equation of the tangent plane. So if I write it, it's nothing but fx at x naught comma y naught times x minus x naught plus fy at x naught comma y naught times y minus y naught minus 1 into is right, so minus z minus z naught is equals to 0. So that will give you the equation of the tangent plane. So z naught is what? F at x naught y naught. So that will give you the equation of tangent plane. Okay, passing through this x naught y naught z naught. Now we are talking about the horizontal tangent plane. Okay, so how would you look at in the horizontal tangent plane? So let's consider this in the space. You can consider some of the mountain. Okay, and let's say like, okay, so this is a kind of mountain. Now if you want, so where will be that horizontal tangent plane? You can have here, here. What other part? Here and here in the down. So this you can understood like valley bottom. Okay, and that you can understood by the mountain peaks. Okay, so where you can find out some tangent plane, horizontal tangent. Okay, so this is how, so this is going to be, you can say, understand like this is a local maximum. It's a local maximum, this is a local minimum, this is a local minimum downward. Okay, so this is how it will be generalized to this. You can have the mountain in the space xyz space. Okay, right. So now, so we can expect now similar extension here for the two variables, and then you can extend this local maximum minimum concept to the 3 variable, 4 variable, and so on. But they are not easy to handle, I can tell you. Okay, right. Now, so as we have discussed for the function of single variable, you will have the similar flavor here. Okay, when you will say it's a maximum or minimum, okay, if certain thing happens. Okay, right. So let's have this here is definition. Let f of x, y, so read carefully. Let f of x, y be defined on a region R containing the point A, comma B. Then we say that f of AB, the f value at the point AB is a local maximum when certain thing happens. If you are able to obtain an open disk centered at the point AB such that f of AB lies above all f, means f value at AB lies above all the values of f or the point which are lies inside that disk. Okay, so it looks like here, what you will look is in the, if you look at the space, so in the space, the disk now means it's not a circle, or not, disk means you have a, what do you mean by disk is it's a circle including all the points inside. Okay, then you will call that as a disk. Now, if you have a sphere, so sphere also, okay, if you include all the points inside, okay, ball, it is known as ball. So if you look, if you try to capture the same thing in the three variables, you can look at here all the spheres. You take a sphere where all the points value. So it's here f of, let's say, a comma b comma c. So you take any point on the sphere, you take a centered at this, that should be greater than equals to f of x comma y comma z. And that looks like, okay, at the peak, you will see any sphere you containing that point. So you will find that f of ABC is greater than equals to f of x comma y comma z. So it's a locally. Okay, again I'm telling you locally, because here it is something different. Here is something different. Here is also something different. We're not talking globally, we're talking locally. Okay, so in the 3 dimension, this disk will convert it into the ball. Open ball means, open means it does not include boundary points. Okay, that means it's an open. Okay, right. So in the disk, it is not it's not consisting of the boundary point of the circle, only the interior point. Okay, so f of AB is a local maximum if you are able to identify a disk centered at AB such that f of AB is greater than equals to f of x, right? For all domain points. So similarly, you can talk about the local minimum. Okay, so f of a comma b is the local minimum value of f if f of AB is less than equals to f of xy for all domain points xy in an open disk centered at AB. I think it is now self-explained. Okay, right. Now, as previously mentioned, the interior extremum theorem can be extended to now function of 2 variable or 3 variable and so on in the similar fashion. How? So what here is, if f of xy has a local maximum or minimum value, we will say it's a, see, when a function attains maximum or minimum locally, okay, we will say it has local extremum. Okay, so later on we will check it's a maximum or minimum. Okay, so f has a local maximum or minimum value at an interior point AB of its domain, and if the first partial derivative exists, then the both first order partial derivatives will zero. You can see this is simple application, or you can say corollary of the interior extremum theorem. Okay, how? So what it says, it's given that, let me, you will have the flavor as well. So given that f of xy has local extremum, okay, either minimum or maximum at a comma b, at point a comma b, and a comma b is an interior point. Okay, now let's define g function. G of x is equals to f of x comma b. So we are fixed by y equals to b. Okay, and this is now function of x, and it has a local extremum at a. So then local extremum it has at a point, and a is an interior point. Okay, so the interior extremum theorem tells you that g dash of a is 0. Okay, that interior extremum theorem tells you that extremum theorem implies z dash of a is 0. But what is z dash of a? It's nothing but fx at x a comma b equals to 0. by chain rule. Similarly, you can define h of y is equals to f of a comma y. And then you can again apply the extremum theorem that will also tell you fy at AB. So indirectly what it says that you have to collect all possible interior point inside the region where all the first order partial derivatives vanishes simultaneously, not individually. Simultaneously, both should vanish. Okay, so those points are local extremum points or critical points that will be told, that will be said as critical points or extremum points. Okay, right. So that is a application of interior extremum theorem. Right. Now this again, you can increase one more dimension here everywhere, and the similar result will be hold true. So I'm not going through with that. Okay, so first derivative test for extremum also can be extended to the third three variables where you have fx at a comma b comma c equals to 0, fy at a comma b comma c equals to 0, and then fz at a comma b comma c equals to 0. You can extend as many dimensions as you want. Okay, right. Now, so now let's define the definition of critical points. And here you will see one more definition, which is known as saddle point. Okay, that we will come. Okay, that we will come. See, you have seen in the function of a single variable, there are three possibilities. Either maxima, right, or minima, right, or point of inflection, right, point of inflection. Means you are able to identify an interior interval there where both side points are exist. Means you cannot say whether it is at C, it is lies above or lies below. Okay, whatever the disk you take, or whatever the interval you take open here, right? So if you recall here, something like that, and you have here is point of inflection where you have first derivative 0, second derivative 0, and third derivative is 0, right? If third derivative is if third derivative is non-zero, okay, then you will say it's a point of inflection. Now, otherwise, if third derivative is 0, then you have to check the sign of fourth derivative. Okay, you have seen higher order derivative test here, right? Okay, so here you have three things: local maxima, local minima, and the two variables or three variables and so on. You have the saddle point. Okay, how would it looks like? It will make clear. Okay, so if I go back and stay with this type of figure, so let me have this is here. Something like you have like this, or not this. So have like this. So this is a point. Okay, this is a point where you find out any open disk, okay, or any open ball, okay, where you will have both apart. Okay, so let me give you the definition, then I will come back to you. So here it is very clear. You will have the horizontal tangent plane, okay, which where you can decide that local maxima. Okay, but here you can't. So here is the definition. So critical point, again, we are talking about an interior point of the dome where both first partial derivatives are either 0 or where one or both of first order partial derivative do not exist. Okay, so either the first partial derivative do not exist or both vanish together. those points are called as, those interior points are called as critical point. Okay. Now, saddle point is a differentiable function f has a saddle point at a critical point. So, very first thing, you can only talk about a point which is going to be possibly saddle point whenever it is a critical point. So, first you have to identify whether AB is a critical point or not. Then you will classify it either it's a local maxima, local minima, or saddle point. Okay. So the necessary thing is it's a critical point. If what you have is in every open disk, you take whatever open disk centered at AB, there are points where f of xy lies above f of AB. Some values are greater than f of AB and some values are less than f of AB. So then the corresponding point on the surface is called a saddle point of the surface. Now, I think now this is clear to you in this picture why I have told you that this is going to be the saddle point. Means whatever the open disk you will choose here, okay, whatever the open disk you choose, okay, whatever the open disk you choose here, you will certainly find some of the points beside which is lies above, and somewhere here in this here you will have the lies below. Okay, right. So now let's take some examples. So find local extreme values of the following functions: x square plus y square and y square minus x square. Okay. Now let's say let's z equals to x square plus y square. Okay. Now if you draw the graph of this, okay, if you draw the graph of this, what it will be? Z equals to 0 is x is origin. Z equals to 1 is x square plus y square equals to 1. It's a circle. So it's a circular bowl. Okay, it's a circular bowl. Lies above the xy plane because z is always greater than 0. Okay, now see, by looking at the graph, you can certainly decide what will be the minimum value. Right? It's going to be the lies above xy plane and touch the origin. That's going to be the minimum value. What about the maximum? There will not be any maximum you can look because you can extend it as long as possible. Okay, unless you mention that you are cutting with the plane somewhere, okay, with z equals to a, okay, or you have this 0 less than equals to z less than equals to, let's take a. Okay, z equals to a, this is f. If I not mention this, means this is a very large ball. Okay, right. Now we are interested in finding the its extreme values. So let me f of x comma y is equals to x square plus y square. So for the point of extremum, what you need to see, the first order partial derivative vanishes. So together fx is 2x, fy is 2y. Now that extremum theorem tells you that fx equals to 0, fy equals to 0 only if x equals to 0 and y equals to 0. If both y equals to 0, or you can say, means this implies 0 comma 0 is a point of extremum or local or is a critical point. Is a critical. And now you can also look at f at 0, 0 value is 0, right? Which is less than equals to f of x comma y. whatever the disk, upper disk you take, centered at 0, 0, you take any centered disk at 0, 0. Okay, you take any centered open disk at 0, 0, that any f of x, y values are always lies above this. It's very clear. So it says that this implies 0, 0 is a local value. Okay, right. Now, so this is decided. There are no other points where both first order partial derivatives vanishes. Okay, and what other thing you have realized? Here is first order partial derivatives are continuous, right? And so function is differentiable. So means what? Means there is no point where the first order partial derivative fails to exist. Okay, so those points are also known as critical points where the first order partial derivative does not exist. So that's also not applicable here. Okay, so all the first order partial derivative exist and they both are 0 only at 0, 0. Now, another example is you have this is w is equals to y square minus x square. Okay, now if you look at, so again, this is a function, it's a nice function, it's a polynomial type, right? X square, y square is going to be a differentiable function, whatever you want. Now, dou w by dou x, what is wx is minus 2x and wy is equals to 2. Now, they are continuous, right? Wx, wy all exist everywhere, so there is no point where they fail to exist. Now, wx equals to 0 and wy equals to 0. Both only at origin. Okay. Now, we have to say what is the nature of this function near 0, 0. So 0, 0 is a critical point. So this implies 0, 0 is a critical point. 0, 0 is a critical point of term. Now you take a centered disk at 0, 0. Okay. So what it includes? It includes as well as the points along x-axis and also points along y-axis. So what is the nature of the function along x-axis and along y-axis? Now along x-axis means y is 0. Okay, so w is equals to y square minus x square, so minus x square means less than equals to 0. Along y-axis, x equals to 0. This implies w is equals to what? Y square, which is greater than equals to 0. So it is equals to 0 only when y equals to 0. It is only 0 when x equals to 0. So there are infinitely many points. You take any disk, okay, any disk centered at origin. So some of the points will falling from the x-axis and some points always falling from the y-axis. Okay, so and you can see f at 0, 0 value is what? Is y square minus x square. So w at 0, 0 is 0. So you have the points w at xy. Okay, so what these two results shows you that w of x comma 0 is w of x comma 0 y 0 is less than equals to w at 0, 0, and w of y comma 0, sorry, not y comma 0, so 0 comma y is greater than equals to w at 0. And these are infinitely many points lying in the disk. centered at 0. Okay, so what it tells you that this implies you take whatever the disk. So that disk will include the points like this as well as like this. So this tells you that 0, 0 is a saddle point. Neither local maximum nor local minimum. Okay, right. Now, we have the second derivative test and some of the problems. So we will look at them in the next session. So if you have any doubt, you can ask. Yes.
Sir, actually, I'm having a doubt, but it's not related to this lecture. Like it's related to some other question.
Okay.
Yes.
Okay. So let us let us wait for other doubt. With like if you have someone else having doubt, then we will discuss. Okay. Okay, Chetri.
Yes, sir.
Okay. If someone has doubt, you please ask. Okay. If no doubts, okay. You can ask Chetri.
Sir, there is one function. Let us suppose that it's f of x, y, and we are required to find that it is differentiable or not. So what I did is I just found its partial derivative, and I tried to look like it's continuous or not. So I found that at point 0, 0, it was not continuous. But when I was trying to find the limit using the formula for finding at specific point, I found its limit to be 1. So, like, is it possible?
See, I don't know which particular function you are talking about, but the thing is, see, limit, see, there are limit may exist, function may not be continuous. Function may be continuous, but may not be differentiable. Okay, reverse way is always true. Differentiability implies continuity, continuity implies the existence of the limit. Okay, similarly,
Means-
in the differentiability, if the function is differentiable, then it has to be continuous. Continuous means it has a limit and that limit value is equal to the function value at that point. Okay, now you are talking about like the first order partial derivatives are not continuous at 0. Some of, right? One of them at least. Have you found,
Like, sir,
have you got that?
actually, my doubt is I found the partial derivative with respect to x, and at point 0, 0, its limit was not, its limit was getting infinity. But when I found limit at 0, 0 using the like formula that limit x tends to x, y tends to 0, 0, f of x naught plus h comma y naught, like using that formula,
Okay.
I got its
Okay.
limit. So is it
So
possible?
means somewhere you have, no. Somewhere then you have done some wrong stuff in your expression of this finding that's fx. You have to check carefully that back formula. You have to either simplify it, maybe somewhere you have that mistake. It is not possible, right? See, first order partial derivative, it exists through the limit definition, it should exist. It will not, it is not possible that that fundamental definition what you are applying at 0, 0 is f of h comma 0 minus f at 0, 0 divided by h limit exists means the function partial derivative exists. Continuity, of course, that continuity is the next thing. Okay, continuity means the function value, fx value at 0, 0 that you are finding, that is 1. Okay, Now, okay. So yes. Your point is okay. Now I'm getting it. So first order partial derivative at 0, 0 value is you're getting 1, right?
Yes, sir.
Okay. Now also you have got the expression means suppose see that for non-zero xy you have derived some expression of fx of xy, right? That you are trying
Yes, sir.
to identify whether that limit exists or not. That is possible. Yes, that is possible.
Like
Okay.
it can
So
be different,
derivative
right?
may exist. Derivative may exist, may not be continuous. No. Okay. If the function, if the limit exists, but I think you should share your that notes with me. Okay. Because if you have that limit exists there, that value, I means that fx. That limit extends to 0. If it is continuous, that limit exists or not? Yes, that is possible. Yes, that is possible. Okay,
Okay,
you
sir.
share with you share that those notes with me on my mail. Okay.
Yes,
Okay.
sir.
The
I
final
would.
expression of your final expression of your f of x comma y, how it is defined, and your steps for deriving the fx and fx at 0, 0 also means these three things you just do mainly. Okay.
Yes, sir. Thank you, sir.
Okay. Okay, fine. Thank you then. If you have any other doubt, you can ask. Okay, thank you.